Welcome to our Hack in the Box talk, JOP ROCKET, bypassing DEP with jump-oriented programming. Hi, I'm Dr. Brizendine. I'm the director of the Verona Lab, and I'm also the creator of the JOP ROCKET. I dabble in being an assistant professor of computer and cyber science, and I'm interested generally in code reuse attacks, software exploitation, reverse engineering, and so much more. I have a PhD in cyber operations, and I'm honored and privileged to be joined by my co-speaker, Austin Babcock, who is a graduate student studying computer science and cyber operations. He is a security researcher at Verona, where he works with me to develop a novel shellcode analysis framework funded by an NSA grant. He's a longtime contributor to the JOP ROCKET, and so skilled is he at jump-oriented programming, you could probably call him a JOP whisperer. He's interested in software exploitation, fuzzing, reverse engineering, and bug bounties. So let's get on with it. Jump-oriented programming. Well, firstly, we'll introduce jump-oriented programming, and then the JOP ROCKET, and then Austin will show us how we can manually craft a JOP exploit to bypass DEP and some various tips and techniques associated with it. And then we'll see how we can remove the human labor element and do it all through automation. Next, Austin will show us, instead of bypassing DEP, well, what if we just simply avoid it and also avoid the need for shellcode and instead just do all that shellcode action directly inside of the JOP exploit? Hey, we can do it. And then finally, novel dispatcher gadgets. That's a very important topic because this helps to make JOP much, much more accessible, because previously the dispatcher gadget was kind of uncommon and now much less so. So pretty big contribution there. So let's get on with it, the background of JOP. Now, it's been around for about a decade in the academic literature, but very sparse, very minimal, very little activity. And really more theoretical, no working JOP exploits to learn from, and even claims that had never been done in the wild. Much of the actual practical information on JOP totally and completely missing. Things that Austin and I have had to develop through experimentation and trial and error. So we've taken something that's been out there in the academic world and theoretical and made it more realistic. And we'll see some real world exploits later on with JOP that we've done. So we introduced the JOP ROCKET at DEF CON 27. We did a full JOP exploit to bypass DEP. But since then, we've expanded it tremendously, introducing automation and also the Two-gadget Dispatcher, which you'll hear more about shortly. Now, there are some different paradigms or different ways to do JOP, and we're going to focus on the first one, which is the dispatcher gadget paradigm, where we have a dispatch table containing addresses for functional gadgets, and these are dispatched. The other way to do it is the bring your own pop jump paradigm, where we continuously load the address of the next gadget and at the same time also do the more substantial operation. So it can be very chaotic and very twisted, maybe not too practical. Another approach that I came upon recently, used in some exploits for the Sony PlayStation 4 and FreeBSD, is this variant approach. There's no title name for it, but basically combination dispatcher functional gadget, and it does the dereferencing and the substantive actions simultaneously. So in this case, RAX points to the dispatcher table and we can access different indexes within it. So let's review some key elements. You'll hear a lot about these later on throughout the presentation. So the dispatch table can be anywhere in memory, the stack, the heap, wherever. And you'll have addresses to the functional gadgets. In between them, you'll have padding. And then the dispatch or a gadget will predictably modify an index into the dispatch table and at the same time dereference the same register. So it's kind of like a program counter that allows us to move from one entry in the dispatch table to the next. And each entry points to the functional gadget, which is more similar to our traditional ROP gadgets. They do the more important actions like setting up when API calls. The stack, forget about it. We don't use it for control flow. And that's very liberating. It gives us some much needed flexibility. But we do use it, however, to set up our Win API functions like bypassing DEP. So we don't use it for control flow, but we do use it for our bypasses and other similar things. So let's see this in motion. The dispatcher goes to the table. We have an address there. Let's dereference it. Okay, now let's do it. And then we jump back to the dispatcher, dereference the next, go to the next functional gadget, and then back to the dispatcher. And this continues for however many gadgets there are, and it works quite well. So jump-oriented programming, it is a state-of-the-art advanced code reuse attack. Not widely used, but we're not trying to claim that this is the next best thing that's going to replace ROP, because even though we present a solution to the dispatcher problem with the two-gadget dispatcher, making it much more plentiful, it's still not always going to be viable. But at least now, with the two-gadget dispatcher and with the JOP ROCKET and the JOP Chain Generation, we actually have a fairly decent chance of doing JOP, just not on every binary. Now, at this point, we would like to introduce the JOP ROCKET. And throughout the presentation, you'll see various cats with flammable devices strapped to their back. And these actually come from medieval manuscripts, like that image you see right there. And these cats are hell-bent on trying to set a castle or a city on fire. In much the same fashion, JOP ROCKET takes that inspiration. We're looking for alternative pathways. And we definitely find them. So you might ask yourself, well, why do we need a JOP ROCKET? Why can't I just go inside IDA Pro or Debugger and find everything on my own? It's a good question. Well, with ROP, I mean, we have tools and they work great. But one thing that they do is they look for the C3, the CB, the opcodes for return, and a couple other variants. And so it's not that many. But with JOP, we're looking for 49 different opcode combinations for many different forms. And then once we find them, we're going to disassemble and create multiple disassembly chunks, and we'll search for practical gadgets. And one very interesting thing happens is opcode splitting. So this allows us to enrich the attack surface by finding unintended instructions that the programmer did not mean for it to be there, but it doesn't matter because it still works. So a couple examples right there, and we can drastically increase the attack surface by doing opcode splitting. And of course, this is something that's done automatically. You don't need to be aware of it. It's just done for you. So once we find an opcode like FF, we then go search for what else it could lead to. And if we find that, then we perform classification, classifying them into different categories based on operation and register affected. So all of this happens simultaneously. We've optimized it so it's very fast. It's not an extremely slow process. Now, JOP ROCKET is a Python program, very modular. But one thing I want to emphasize here is if you're going to go after a target application, have it installed and provide the absolute path as an input on a text file. That way you're able to enumerate all of the DLLs and find gadgets for those. Otherwise, if you do it just on the command line with the executable, you won't find all of those DLLs. And if you're doing a very large program like 100 megabytes, then you'll probably want to do the 64-bit Python to avoid memory issues. So let's see how it works with the menu system. So first you want to indicate the registers of interest. So simply R can do that. And then G will go and scan for those selected registers. Or if you want all of them, then you can just do the big G or Z. And then at the scope, you can set, if you want more than just the image executable, you have that option. And then you can specify mitigations that you want to avoid, or to just simply enumerate the mitigations. And then B will allow you to show or avoid particular bad characters. J is the JOP Chain Sub-menu, which we'll see later on. And then once you do the G option, it's found and is classified everything. So it's just simply a matter of printing your results. And here we go with the print submenu. So many different options. And if you want everything, just do the big P, but you can also specify specific registers or operations. Here are some sample results for the icon making software we'll be looking at later on today. And we can see we have a great number of results saved to a directory, and each is named after the operation performed and the register affected. And let's look at some of the results there. We see that we have add EBX, and so it has add with carry, and other various forms of EBX.
So we've learned all of this about JOP, how it works, but how do we actually want to apply this to making a real-world exploit? That's the fun part of any exploitation technique, is actually using it. And that's a bit of a loaded question, so part 2 is going to have a few different topics here. First, we're going to talk about selecting our dispatch registers and our dispatcher gadget. We'll talk about JOP's purpose in an exploit. We'll talk about different things JOP is able to do, like avoiding bad bytes, stack pivoting, writing function parameters to memory, performing function calls. We'll also talk about JOP NOPs, and then we'll show our demo exploit. So on the first topic, choosing dispatch registers. We want to choose a register for our dispatcher gadget address, and we don't actually want to, we have to. So with our dispatcher gadget address, the register we choose will determine which functional gadgets we can use, because our functional gadgets have to end in a jump or a call to this register. We want to choose the register such that we have good functional gadgets to work with. If we have a specific one that's very useful, or if we have a lot of them that are very useful with little side effects, we would prefer to choose that register if possible. We can use gadgets from other registers that are a little bit more complicated, like those on the bottom. However, if we can avoid some of those side effects or weird instructions, we would probably prefer to do that. Also, we need to choose a dispatch table register. So our dispatcher gadget is pretty much going to tie us down as far as which register we can use for that. If we have this dispatcher gadget on the top here where we're using a jump dword pointer EAX, we pretty much just have to use EAX as our dispatch table register. So we want to make sure this register is compatible with our functional gadgets that are available when possible, but at the same time, if we're making a bunch of compromises and using a dispatcher gadget like the one on the bottom, where we have a lot of side effects, then we're going to run into some troubles, because each time we execute our dispatcher gadget, we're going to get those side effects. On the topic of selecting a dispatcher, we were talking earlier that modification to our dispatch table has to be predictable, and what's more predictable than adding or subtracting the same value every time? So these are nice dispatchers to use. We're just going to put all of our functional gadget addresses in our dispatch table in a row. If we have more than 4 bytes being added or subtracted, we'll add some padding. And the only difference is, if we're doing subtract, we're just going to put them in a reverse order. And we don't even have to worry about the mental overhead of putting them in reverse order manually, because of something like Python, we can just do a list reverse on the list of all of our functional gadgets. When we're selecting a dispatcher, you want to keep in mind how much memory we have available for our payload. So if we have a dispatcher that is going to be something like that one on the right, where we have add EDI hex 10, we have to have a lot of padding in between each functional gadget, and we're going to take up a lot of space. So once we get our dispatch register set up, what do we want to do with JOP? Well, with JOP, we want to execute when API function calls, and we're going to get around DEP using those. So the traditional method would be to use something like VirtualProtect or VirtualAlloc to make a memory region executable, and then we would execute our shellcode afterwards. Another method that we can do is shellcodeless JOP, where we're not necessarily bypassing DEP as much as we are just avoiding it altogether. We're actually using the function calls themselves to perform the actions that maybe our shellcode normally would. With our Win API function calls, we have an example of the parameters that we would supply here for VirtualProtect. And when we have values for parameters that we know at the time of writing our exploit, things that can be hard-coded, we can just supply these into the payload themselves. However, with things like parameters that have to be dynamically generated based off of memory locations or bad bytes, we need to supply dummy variables that we can later overwrite using JOP. So talking about bad bytes is one of the reasons to supply dummy variables. So bad bytes is the idea that if we have something like a string buffer, when we start encountering a null byte or a carriage return or a line feed, our string will stop being read in, and then we can no longer use it as a payload because it's not getting read into memory. So we can't supply those bytes in our payload, so we need to get around that using JOP gadgets. One way we can do this is with an XOR gadget, although there's plenty of other ways: add, subtract, negate. But XOR is a good example. So with XOR, we start by popping an XOR key, and then we pop the corresponding value into another register. Again, that doesn't have to be a pop, it just has to get loaded into the register somehow. However you are able to do it with the gadgets you have available. And then once we perform that XOR, we're going to load that final value into a register, and we haven't actually supplied that bad byte value in our payload at all. Another place bad bytes can show up is in functional gadget addresses. So the addresses of the functional gadgets themselves might have a bad byte, like these stack pivots on the right have a null byte at the beginning. But if we want to still use them, what we can do is load their address into a register and then jump to that register rather than putting them in the dispatch table themselves. One other thing we need to do often with JOP is stack pivoting. So with stack pivoting, we need this for all sorts of things: popping values, getting the function parameters to be at their correct location, making sure our overwrites happen at the same spot. It's used for all sorts of things. So stack pivoting forward is fairly easy with JOP, where we need just pop instructions. We'll cut it. Each pop instruction will increment ESP by 4. So here we have 2 pop gadgets moving ESP 8 bytes. However, moving backwards is a little bit more difficult. The gadgets that are suitable are harder to find, and it is true that the push instruction does subtract 4 from ESP. However, we're also overwriting values on the way as well, which might not always be so useful for us and might actually cause problems. Although the push instruction can be used to our advantage as well. Even though it's not so great for stack pivots, we can still use it to overwrite parameter values. So if we have dummy values that we're using to hold the place of a value that needs to be dynamically generated, whether that be for bad bytes or some other reason, we can load that value into a register, stack pivot 4 bytes above the location we want to overwrite, because ESP or push is going to overwrite to ESP minus 4. And then we will push our value onto the stack there. And now we have one of our functional parameters. We have one of our VirtualProtect parameters that was a placeholder written with the actual value there. And if we want to do a lot of pushes in a row like this, we can set up our stack in a special way here, where we have the same distance between each encoded parameter that we're dealing with, and then our dummy variables. The distances between each pair there are the same. So that way we can keep on using the same distance stack pivots each time. So for an example of that, we have a pop EAX here, popping the first encoded parameter off the stack. We're going to avoid bad bytes by using an XOR, and that's why it was encoded in the first place. We will pivot ESP using 3 pop EBX gadgets, and then we overwrite our placeholder in memory. Afterwards, we're going to pivot ESP backwards, and then we can keep on repeating from step 1, just doing that same process over and over using the exact same gadgets. We don't have to search for any different stack pivot gadgets or anything, because we've set up our stack in this way here. So, moving on from push, we have another way to overwrite dummy values, which is with the move dword pointer gadget. And these are less commonly found, and we can also use different types of gadgets. So, move dword pointer is 1, but we can also use things like add dword pointer or subtract or things like that as well. But move is a pretty good one to demonstrate here. We are going to have to use 2 registers to set aside for this gadget, which might be a bit of a problem with JOP sometimes because we have 2 already set aside for our control flow. But with move dword pointer, our first register is going to hold the address that we want to write to, and our second register is going to hold the value. And once we execute this gadget, we will overwrite our second parameter that was a placeholder in our example VirtualProtect here. One thing to note here is that we don't need any stack pivots at all, which is nice. Once we have all of our parameters set up in our function here, we can pivot ESP to the beginning of them before our function call. And then to call that function, we can grab the function pointer and then dereference it. There are several different ways we can do that. We have a couple of examples there. The most simple, straightforward one would probably just to be the top gadget there, where we just do a jump dword pointer EAX. One last thing before we go into our demo is we might not always know when we're setting up our JOP exploit where exactly the dispatcher gadget, or not the dispatcher gadget, where exactly the dispatch table is going to be. So if we don't know the exact location, but we have a pretty good idea, we can kind of guess the location, and we're going to use JOP nops in order to pad it out the dispatch table. So we're going to make our dispatch table very large with a bunch of JOP nops. However, these instructions are just an address to an instruction that's just going to jump back to the dispatcher gadget. So we're going to perform no operation with each one and just keep on jumping down the line if we guess anywhere in there until we get to our actual dispatch table. One thing to keep in mind is that this is an address. It's not like a shellcode NOP where it's just an opcode. So we do have to guess the alignment correctly there. If we don't guess the alignment correctly, we're not going to get the correct address, and we're going to probably get an access violation. Also, if we have padding with our dispatcher gadget, we need to specialize our padding because we can have multiple entry points to our dispatch table depending on which NOP we guessed. So here we have the top JOP NOP, which is kind of fun to say, but we guess our location of the top JOP NOP, and then we enter our dispatch table at one point. So here, top one, enter at that top point. However, if we guess the second one, we'll enter our dispatch table at the second location. So we need to specialize our padding so that we can account for that. And one easy way to do that is just to keep on repeating that previous gadget address over and over until we get to our next gadget. So we'll take a look at a demo of an actual exploit used with JOP. So we'll see some stack pivoting, or using JOP, we'll see some stack pivoting, we'll see some avoiding bad bytes, we'll see some writing parameter values, but we won't go too deep into the weeds here. We'll just show you the big ideas. So we can see with our exploit here, we're going to start with a stack pivot. We are going to do a move ESP to start it out, and then we're going to add an 800 value 2 times. So we're going to add 800 twice. After that, we're going to start XORing bad bytes out so that we can push function parameters. So we're going to see an XOR, and we're going to see 2 VirtualProtect parameters being pushed here. So here we can see XOR ECX to get a bad byte value into ECX. And then later, we're going to push that along with EAX as 2 of our functional, I keep saying functional, 2 of our function parameters here. Afterwards, we can see step 3 here is keep on pushing parameters. We're going to keep on doing what we were doing, XORing bad byte values and pushing more parameters to set up our VirtualProtect function call. So we have 2 more pushes here, and now VirtualProtect is almost ready to go. So at this point, we're going to stack pivot on over to the start of our VirtualProtect parameters. We're going to grab that address to VirtualProtect, the pointer, and we're going to dereference it to get the actual address to VirtualProtect. Now, once we have that dereferenced, we can call the function. We can see our parameters in the bottom right, and once we return, we'll return to our shellcode, showing a proof of concept just opening Notepad, but that will show that we can run shellcode using JOP, bypass DEP, And that's really cool because that's rare in the wild. So we don't see that often in the wild, and that's a cool thing to do.
Our next topic deals with the automation of JOP chain generation. And when you approach something like this, it really makes sense to reduce it to a recipe. With return-oriented programming, we create that recipe centered around push add. So with push add, we populate all the registers with specific values such that when we perform push add, the stack is all set up for our win API call, and it makes the win API call is part of that technique. Now, with JOP, that's just not possible because, for one, we can't use push add, and also with ROP, every gadget is going to end in a return, but with JOP, it's going to end in a jump or a call to one of several different registers. And keep in mind what this is it's a functional gadget jumping to the dispatcher. And so we'll have certain registers set aside for those purposes, and those registers need to remain deconflicted, and the other registers, we can use them to do things like setting up our stack parameters. So it really seems that all of this would maybe make automation infeasible because all of these different registers could be used for different purposes, and how do you keep track of all of that? It sounds like too much, except, well, maybe it's not, because it really begs the question then, can you simplify JOP? Do you have to embrace the kind of manual technique that Austin showed you, or is there a simple path that could be an alternative? And there is. And it's utilizing a series of multiple stack pivots. So let's check this out. We have a buffer overflow, we have an SEH overwrite, whatever the case may be. And at that particular moment, ESP points to a certain value. So it's 1, 2, 3, 4 right there in our example. But our stack parameters are quite a distance away, almost 5,000 bytes. And what we can do is we can precisely calculate that amount and do a series of stack pivots, and look, lo and behold, we have reached it. So by precisely figuring out that location, we can adjust our padding and different stack pivots to enable us to get there. So here's another example, a little bit more technical detail. So we have various add ESPs, and collectively they allow us to get to almost about 1,320 bytes. And then next, we pop into EAX a pointer to VirtualProtect, which JOP ROCKET finds for you, and then we make a dereference call over there. Now, this is something that the JOP ROCKET, it takes care of all of this, and it makes sure that all the registers are deconflicted. So specifically how this JOP ROCKET will do this is it'll try to set up registers for the dispatch table and also for the dispatcher gadget. And we start things off with ROP just because from an automation standpoint, there's pretty much a guarantee that we can do that for every functional gadget, a functional gadget ending in a particular register. And what we want to do with JOP ROCKET is enumerate each and every possibility. So functional gadgets ending in EAX and EBX, ECX, EDX, so on and so forth. Because depending on the registers available, some of them may work, some of them, there just may not be enough gadgets. So we look and we try all possibilities. So it really works on the premise that functional gadgets are going to end in the same register. Now, of course, manually, you can switch that if you want to, but from an automation standpoint and just a general best practice, if you can stick to one register, it's going to make your life a little bit easier. Now, what JOP ROCKET will do is for each functional gadget ending in a register, it'll try to find 5 different unique chains. So if for some reason one doesn't work, okay, then we have some other possibilities that we can consider. So check it out. We go to the JOP Chain Sub-menu. The first thing you want to do is hit S, and that'll do the scanning for the JOP gadgets and also ROP gadgets too to set it up with POP. We can specify the desired stack pivot amount. And this is important because if, let's say, functional gadgets ending in ECX, there may only be a large stack pivot, but if you're searching for only a small stack pivot amount, then it may not find anything. So try to assess and determine the desired minimum and maximum. And keep in mind, it doesn't need to be exact because we can make up the difference with padding. Just make sure you get the exact absolute minimum that you need. And then from there, G will go and get the gadgets. You can also, if you want to, you can change the number of JOP chains that are generated per register. So if you want more or less possibilities, hey, that's an option. So this is the same exact thing that Austin did earlier from his manual exploit. And we've done it with JOP ROCKET, and we have a chain for VirtualAlloc. It's created one that has everything we need to utilize the stack pivot technique. And here's one for VirtualProtect. We'll look at this more closely in a second. But the great thing about this is if we introduce the actual vulnerability part of the code, then this pretty much works. So everything that Austin did could be reduced to doing it via JOP ROCKET, the JOP Chain Generation. We'll see that shortly with a live demo. So let's break it down. So we'll kick things off with some ROP. We'll load our dispatcher gadget, load our dispatch table, and then we'll actually start the job by jumping to EDX. And then from here, it's just a series of stack pivots, 894. We do it again. And now we're going to load EAX with a pointer to VirtualProtect, and then we're going to dereference that. And then from there, that's when we actually make the call to VirtualProtect. And so we want to then have all of our stack parameters, which we do. And if everything is set up and there's no little special issues you need to address, then you have a good exploit. JOP ROCKET also provides some other good starting points for you there. And so without further ado then, let's see this actual exploit live in action. Okay, so let's do a stack pivot of 894. We get back to our dispatcher gadget. And then we're adding 12 to EDI. And then another stack pivot of 894. And then back to our dispatcher, adding 12 to EDI. And now we're going to pop into EAX, a pointer to VirtualProtect. Back to our dispatcher. There we go, adding 12 to EDI. And then now we're going to make a dereference jump to VirtualProtect contained in EDI. Let's check out EAX. Okay, so we see a VirtualProtect right there. Now let's check out our stack values. And we have our stack parameters. Yeah. And let's check out the return address, which is the actual shell code. And we're walking to PEB. So yeah, that's shell code. So let's see if we can actually do it. Okay, we're in VirtualProtect. We got it! That Rocket Cat got her shell code. Austin created a real-world JOP exploit attacking icon-making software using the JOP stack pivot technique. Now, he did it all by hand, but actually the JOP Rocket would have found a very similar chain. So let's see what he did.
Hey, I'm back. I'll be taking you through an example of an exploit I created on a binary in the real world, a binary called IcoFX 2.6. It's an icon editor with a vulnerability that allows you to craft a malicious icon file. And I've created a JOP exploit using a similar stack pivoting approach that the automated generation does. So, although I did build this exploit from the ground up, comparing it to the automated JOP chain generated for this binary, I actually could have saved some trouble that I had finding gadgets at the beginning, because a lot of the gadgets that the automated chain generated were actually the same that I was using. So that would have been a really good starting point for my exploit. However, even with that, this was still a challenging binary, and some of the gadgets that were used had to have some special considerations made. And I'll talk about that here in the next few slides. So, our dispatcher gadget. So, our dispatcher gadget is a little bit weird. It's kind of nice, but we do have an add with a dword pointer EAX is the value that we're adding to our dispatch table. So we do need to set up EAX to point to a value that we want to add to ECX. So that does need to be a valid memory location. Also, with our stack pivoting gadget, we have a similar problem where we have a dispatching, we have a dereferencing with an offset based off of EBX. So we want to make sure that that value that goes to is going to be writable so that we don't get an access violation there. And even though we do have some of these weird gadgets, we can still make them work. And that's just part of the fun of the JOP. Every exploit is going to be different, and we're going to have to do weird things sometimes, and that's kind of fun. So another thing that we have in this exploit is we have our dereferencing gadget here, and this dereference has an offset in it, and that's really not a problem at all. All we have to do is make sure that we're adding that offset to our pointer in our value that we supply there. So we can see our screenshot from our code in the bottom right. We just have the pointer to VirtualProtect, and then we're adding that 71 offset, so we take care of that with our gadget. So look at the video here. We're going to start with a top ECX gadget, and that's just the start of our ROP setup chain for our JOP control flow. So we're setting up our control flow with ROP, and then we're going to perform JOP in order to do our stack pivot. We will load our malicious icon file. We'll go to our first breakpoint, that ROP setup chain. And one thing to note with this setup chain is that we're actually dynamically grabbing the addresses of our dispatcher or dispatch table, and then also that address that we use for EAX for our value to add. We're going to dynamically grab that too, doing some self-location techniques just for added stability here in case any of those addresses change. If we didn't do that and one of those addresses did change, then we would run into problems. So we can see after we set up our EAX register, we're going to be pointing at a value. If we look in the bottom left here, we're going to be pointing at 4 with EAX. So that 4 value is what is going to get added to our dispatch table each time our dispatcher executes. We'll skip over some of the additional setup here, and then we'll skip to our JOP section or stack pivoting. So starting JOP, we are going to stack pivot 40 bytes using this top EBP gadget over and over. So you can see here, we're going to go to our breakpoint, we're going to do our pop EBP, and every time we execute this gadget, we're going to get closer and closer to our parameters. And we can see us stepping through our dispatcher gadget, and that's working successfully too, so that EAX value is set up correctly. So since bad bytes weren't an issue in this exploit, that's why we're using the stack pivoting approach. We have our VirtualProtect parameters all supplied in our payload here. We can see those under VP params. We'll continue approaching that with our stack pivot. Now we've gone through about half of our stack pivots, and we'll just skip through the rest of them real quick. We're ready to dereference our VirtualProtect pointer and call our function. So we will call VirtualProtect here, executing this jump. Now that we're in VirtualProtect, we're ready to make that region of memory executable and execute our shellcode. And we can see now we've popped calc using JOP in a real world exploit, which it's really cool and it's really rare.
Now our talk is about bypassing DEP, but what if instead of bypassing it, we could just simply avoid it altogether and call those Windows API functions directly instead of using shellcode? And that is exactly what Austin will show us how to do.
So I'll be taking you through an example of the shellcodeless JOP technique. We're going to look at an example exploit here. And for an overview of our exploit, we're going to set up our JOP control flow. We're going to pivot ESP, then we're going to perform 3 function calls. So load library is going to give us a handle to the MSV CRT DLL. We're going to use that handle with get proc address to get the address of a certain function within that DLL. and then we'll perform that call in order to perform a Windows command line command. And we'll see what that command is during the demo. So, just like with any just like with any JOP exploit, we're going to set up our JOP control flow. First of all, we're just going to use a JOP gadget in order to do that. And we do have to XOR some values there because we have to worry about bad bytes. However, later in memory, we have a copy of our payload that doesn't have bad bytes in it. It does. However you want to put it, the null bytes that are normally bad at the start of our exploit are included in our payload later in the exploit. So what we can do is pivot ESP forwards to our second copy of our payload where those null bytes are no longer an issue, and then we can pivot 72 bytes and perform the rest of our exploit without worrying about those. So some things to take into consideration with some of these WinAPI calls is that we need locations of pointers for things like strings or sometimes other kinds of data structures as well. If we can help it, we want to try and dynamically generate the address of those certain values. So if we can dynamically generate those pointers, then we don't have to hard code them into our exploit. And if we have something like rebasing ASLR going on, we can actually still do that and supply the correct value. However, we don't have ASLR rebasing in our exploit, in our program, So once we can just hard code that value into the payload, and we don't have to worry about that. But if we were still being the best exploit writers we could be, we would probably want to dynamically generate those so that we have better stability. With those string parameters, another thing to consider is that with some functions, such as load library exw, which we're using instead of the normal load library function, that w means we want a wide character string. And that wide character string is going to be formatted differently. It's got some padding in it. And the encoding there is usually UTF-16 little endian, although that can be OS dependent. So just as a sanity check, we can throw that into something like Visual Studio with C++, and then we can run that debugger in order to just make sure that we're using the correct formatting there. Something else to consider is that we might not always have the pointers to every function that we want to use in our shellcodeless exploit. However, if we have a pointer to another function in the same library, we can get the offset from one to the other. So here we have a pointer to load library exw, and then we'll open that up in IDA, and we'll see the address to load library exw, and then we will see that get proc address is in the same library. It's in kernel 32, so we can actually get the address of that function as well and then find the offset between the two. If we are doing this method, it does lack portability because depending on the release of what OS we're using, we're going to have a different version of the DLL and those offsets are going to be different. However, once we get that offset, we can dereference the function pointer of the one that we have and then add that offset to get the address of the next function. We're going to use that in our exploit here. One last thing to consider is that if we have output from one function that we're using in another function here, so here we have load library, which returns a handle to msv_crt.dll, and we want to use that handle as one of our parameters for get proc address. So we're going to actually get that handle, and then we're going to push it using JOP because we won't know what that value is going to be at the time of writing the exploit. We have to do this at runtime here. So that return address, or that return value is going to be returned into EAX, and then we can do a push EAX gadget there. So again, for another overview of what we're doing, we're going to set up our JOP control flow, we're going to pivot ESP, we're going to perform our function calls, our load library is going to give us the handle, our get proc address is going to give us the address of system, and then our system call will be our actual final malicious action. We'll take a look at our demo here. So we're going to start with our JOP setup section, where we're going to set up our control flow registers. So here we can see we're doing a bunch of pops and some XORs. Once we get that set up, we can see an EDI is the address of our dispatch table, an EDX is our dispatcher gadget. You can see our dispatch table in the bottom left. We're going to perform our stack pivot afterwards, pivoting ESP, that's 72 bytes, to the better location in our stack, where we can supply those null byte values. So here we're trying to get there. And we can see as we execute our add ESP, we're going to keep on approaching that location, getting closer, closer again, and then we're there. After our stack pivot, let's take a look in the code. What are we doing next? Well, first we want to call load library exw. And all of the parameters for load library, we can just put directly into our payload here. So we have our pointer to the MSB CRT string, and in a second, after we dereference the address or the pointer to that function and we call it, we can see that we are using the correct parameters. We have our pointer, and if we follow that pointer in the dump in the bottom left, and a little bit of misclicking here, but we'll follow that in the bottom left, and we can see the actual ASCII values of the bytes there. And we have that padding in between each letter there because we have the wide string. So we actually return to a repair gadget because load library is going to crush one of our registers that we're using for our control flow. So we'll just do a bit of a repair gadget here. And then along with that, we're going to repop the pointer for load library because we're going to use that again for getting that offset to get proc address. So we'll see we're going to dereference that pointer real quick. This is the section of the code where we're doing so. We'll dereference our pointer. We'll grab our offset into EBX, which is actually a negative value. We use 2's complement to find that. We will add those two values together to get the address of get proc address. Now that we have that, we can push our handle that we got from load library, our return value, and then we'll also push our return address for get proc adder. That return address is actually a jump EAX gadget because get proc address is going to give us the address of the next function we want to call in EAX. So we can just return to a jump EAX afterwards. So here we can see our get proc address function is being called. You can see we're using the correct parameters. We'll return to that jump EAX gadget in a second once we execute get proc address. Now we'll jump to our system call. And that's the function system, not an actual system call. And our command we're using for our command line command for this is shutdown/L, which is going to log out the current user. So maybe not the most malicious type of payload here, but it's definitely annoying if you were trying to run this program and you didn't know what was going on. It's going to take a second, but we'll log out our user here. And that's a shellcodeless JOP exploit. So with that, I'm going to pass the presentation back on over to Bramwell one last time.
So our next topic is a very important one, and it deals with novel dispatcher gadgets. And when I say novel, I mean very novel because it's very recent, just the last couple of weeks. So let's review the existing dispatcher gadgets. We have add, we have subtract, we have load effective address. And really at the heart of it, we're predictably modifying, like say we're adding to EBX a value like 4, and then we go and make a dereference jump to the same register, like EBX. Short and sweet is the most desirable because we can avoid side effects that would clobber other registers. Not a good thing. If it sounds like we're asking for a lot, yeah, indeed we are. And understandably, gadgets like this are kind of scarce. And that's a really bad thing if you're trying to do jump-oriented programming and your most important gadget is obscure. So I gave it a little bit of thought, and it just kind of came to me relatively quickly. And what I came upon was expanding it to a two-gadget dispatcher. So what if we could instead add to a register, make a non-dereference, just a traditional indirect jump to a different register, let's say EBP, and then the next gadget, all that it does is make a dereference jump to the first register. And turns out it actually works. So let's see it in motion. Follow that little diamond. Okay, so we go there, and yeah, it works. And we've checked this out through different exploits, and indeed, it does work. So it's very exciting because this opens up a lot more possibilities. Now, instead of needing a relatively obscure gadget, you can find just any gadget that does add, subtract, load effective address, and some other things we'll talk about shortly, and then jump to a different register. And that other register will then point to the gadget that does the dereferencing. And you may be thinking, well, what if we don't have that other dereference gadget? Well, guess what? You probably do. Because another thing I implemented was what I call empty jump dereferences. So in this case, it looks just for a single line. So FF whatever, a jump to a particular line. And these are actually very, very plentiful. And I call them empty because it may exist only as a single line, and you expand it to two lines, and it doesn't exist. And for a medium to large size binary, you're pretty much guaranteed that all of the registers will be represented. Although with EBP, it may actually be something like jump EBP plus offset, but that's something we can easily accommodate as well. And so a lot of results right there. And the great thing about this also is we can also now use call gadgets, because usually with a dispatcher gadget, you don't want to use call because it would continuously add to the stack, which is not a good thing if you're trying to build stack parameters for a WinAPI function. So how we accommodate this is I came up with another gadget where we just simply add a pop right in front of the dereferencing. And so JOP ROCKET will search for this as well. And the good news is this second dereferencing gadget is pretty plentiful. It's not a guarantee like the other one is almost a guarantee, but it's still very, very plentiful. So this opens up tremendous possibilities for potential dispatchers. And the end result of that is now jump-oriented programming is much more feasible. These do come at a cost, though. So instead of reserving two registers with a traditional dispatcher, we will also reserve a third, because we need another register to point to the dispatcher dereference gadget. Now, another thing that came to us recently from one of our co-authors from our Hack in the Box white paper, Andrew Kramer, who's a Dakota State instructor, he said, well, what about using some string instructions to do dereferencing? So don't think about their intended purpose, which is to do stuff with strings. Think about how they are going to predictably increment ESI or EDI or both. So we don't care what their intended purpose is, just that they're going to do that incrementing for us. And also the QD form will do 8 bytes. So 4 bytes or 8 bytes. And I created a little chart down there that shows what does what. So let's see that in action right there. We see an example right here with load SD. And in this case, we actually don't even need any padding because it does it 4 bytes. So we do load SD, jump dword pointer to ESI, and then that points to the dispatch table. Each address is 4 bytes because that's the size of the pointer. And so it's another way to expand available dispatchers. And yes, the two-gadget string dispatcher works as well. Again, it just simply switched it up a bit. So in this case, we would do load SD and then a regular jump to EBP. And then now we dereference ESI in the second dereference gadget. Some other quick various topics. Control flow guard. It's Microsoft's way to enforce control flow integrity. But the thing is, it's done at a compiler level and it's very coarse grained. Now, there have been various bypasses out there. We're not going to talk about this. We're just briefly going to address some ways to maybe avoid it. Because if it's done perfectly, it can make JOP, it can provide some good defense against that. So the things to keep in mind here are, well, a number of different things. For one, inline assembly will not work. Windows 7 will not work, and that's 19% of computers as of the current month. And also opcode splitting will allow us to form a number of different gadgets, JOP gadgets. And so if you get results and it looks like it's going to work, it's probably going to work because what CFG does is it inserts a guard check. And so it can't insert a guard check if it's from opcode splitting. So although you have the ability to exclude results based off of CFG, I don't necessarily recommend that just because you still may find some viable results from opcode splitting or from inline assembly. And that's pretty much all that we have to say. Our goal has been to expand JOP, to provide the tools, to provide the knowledge, and to help you guys do what you do best, to do awesome hacking, and hopefully expand that, not just from ROP, but also to JOP. With that, we'd like to thank you. We will be available in the studio channel if you want to chat with us, and also on Discord.